So good afternoon, everyone. Welcome to the current Power and Energy Seminar Series. So today we have two presenters. One is Jingjing Sun, and the other one is Dr. Jin Zhao. So before introducing the seminar information, so I would like to cover a few like housekeeping. So today we will have two presenters. That means each presentation will run for about 20 to 25 minutes. So if you have any questions, please feel free to type it in and send it up in the chat box or raise your hand so that you will be unmuted at the end. As usual, everyone student taking the 496 or 691 EC class is getting the sign-on recorded and posted on the I think it's my UTK. There's an attendance tracking that the student can track. Okay, so today our first presentation is by Jingjing Sun. So the presentation title is Emulation of Voltage Sag Event of a Data Center Power Distribution System. So Jingjing Sun received her BS degree in electric engineering from Xi'an Jiaotong University in 2016, and the MS degree in electric engineering from the University of Tennessee, Knoxville in 2018. Since 2016, she has started to work towards her PhD degree under supervision of Dr. Leon Tolbert at the Department of Electric Engineering and Computer Science and the University of Tennessee. So her research focuses on data center power system modeling and emulation, application of wide bandgap devices, high efficiency power supply design, high frequency soft switching power converters. So let me turn the presentation to Jingjing. So please go ahead and unmute yourself and share your screen.
Sure, thanks Hantao for the introduction. I will share my screen. Okay, can you see my screen?
Yeah, that's great.
Okay, thanks. Hello everyone, this is Jingjing Sun from the University of Tennessee. I'm a PhD student in power electronics under Dr. Tolbert. And today I will talk about my research on development of a converter-based data center power emulator, and also will show the demonstration of the emulation of the voltage sag event in the developed emulator. So we know that data centers are indispensable for today's computing and networking society and have been constructed all over the world. It is reported that the global data center electricity demand is above 200 tegawatts in 2018. This accounts for almost 1% of the total power demand in the world. So data center is a large large electric load with high penetration in the power grid. On the other hand, as you can see in this typical data center structure, it is a very complicated system with a high density of power electronics and controls. The electrical power supply system actually includes several different stages. Each stage have many power converters, and also the cooling system also have different cooling components. To ensure the whole system operated in a normal condition, the control strategy is also complex. So the whole data center also performs a nonlinear performance as an electric load. Therefore, the influence of the data center's impact on the power grid is significant. So on one side, we know that the dynamic the server load of the data center actually has a dynamic profile, which may result in apparent power demand fluctuation in a short time. On the other hand, during the great disturbances or contingencies like the voltage sag event, the data center system will change its operation mode to ensure the stable power transferred to the server load. This will lead to apparent power dynamic response in the grid. Therefore, it is important to evaluate. It is important to investigate the data center load characteristics and evaluate the grid dynamic performance and transient stability with the data center load. As a result, we will need to develop an accurate data center power model and the according power simulator or emulators to help evaluate the performance. Let's check the existing work first. We found that the existing data center power models actually have many disadvantages. They are either incomplete or incapable of predicting dynamic performance, or some of them have limited availability or flexibility, and the prediction result is not accurate enough. On the other side, for the simulation or emulation platforms, they include the digital simulation tools like the PSCAD or MATLAB Simulink, real-time digital emulators such as RTDS, or analog-based emulation platforms with downscaled prototypes or hardware testbeds. Well, the digital-based simulator or emulators, they are cheaper, smaller, and easy to be installed. However, they usually suffer from instability or convergence issues, and often they ignore the realistic conditions like the control bandwidth, the communication time delay, or the switch noise. Well, for the analog-based emulators, although they are more expensive, heavier, and less accessible, the testing results are more convincing and are usually preferred for engineers. So in our center, a unique converter-based reconfigurable hardware testbed is developed to overcome the issues with the digital simulators or conventional analog emulators. So the HCP platform, as you can see here, is based on multiple converters, and by programming the interconnected three-phase voltage source inverters, we actually can emulate different power elements, such as the generator, battery energy storage system, and various power loads. So it is a good platform to perform real power tests and emulate different power experiments. And and based on this, the HCP platform, a data center power emulator, is developed in this work. So to start with, we need to first identify the data center system circuit and controls. So based on the survey, we found that the AC power distribution system is widely used in the data center market, as shown here. So the AC power is transmitted from the substation, and then there is a centralized UPS used to condition and regulate the AC power. And then the IT equipment will be powered with the AC source, and the power distribution unit is used to split all the AC power into many single-phase AC powers and transfer it to the server racks, finally to the server load while the power supply unit and the voltage regulation module. On the other part is the cooling system. Usually air cooling system is the dominant one. It includes the cooling tower, chiller, water pumps, and the computer room air handler. Also, there are many server fans distributed in different racks. So to ensure the normal power for the IT load and achieve a high power usage efficiency, Data centers often adopt reconfigurable structure and multiple operation modes. So here, operation principle is identified here in response to different voltage levels. So the first one is the normal echo mode. So when the source power from the grid is within the acceptable limit of the system, the UPS is bypassed so that the whole power will not be convert in twice, and a significant power loss can be reduced. Then the IT load is directly connected to the grid. When the source power is, let's say, a grid disturbance like the voltage sag happens, so the source power is not within the acceptable limit, then the UPS switches in to help regulate the AC power and carry the IT load so that the server load is not disrupted. In both these two modes, for the air cooling system are directly connected to the grid. However, when a severe power disturbance happens, all the power failures, all these will be disconnected from the grid. And the UPS backup power from the battery pack will be supplied to the IT load through the DC-DC converter and the inverter in the UPS. And also to maintain the air circulation and the cool temperature within the server room, air conditioning will be kept on with the power from the UPS. So these different operation modes will changes in response to different voltage levels. For the specific circuit topologies and controls that is widely used in the data centers have been listed here. And I will not talk so much about it. And we will, based on this data center system, to build our model and develop the power emulator. So the first step to develop the emulator is we need to have an accurate power model of the system. Since we only care about the dynamic performance within the line cycle, so the average model that neglects switching ripples are built here for each power converters and power components. Because of the space limit, here I only show the UPS model and control. So so the UPS actually is composed of a three-phase boost PFC converter, a DC-DC converter, and the battery pack, and the three-phase voltage source inverter. Accordingly, the average model is derived as here. For the control part, the UPS rectifier is controlled by the peak current mode control, and also the DC link voltage is regulated. For the voltage source inverter, traditional dual loop space vector control is implemented in the DQ rotation frame. And well, for the DC-DC converter, so in the normal mode and the double conversion mode, the DC-DC converter is only responsible for charging or discharging the battery and control the battery power. So only the battery current is controlled, and the current reference is generated based on the power demand from the top level control. While in the battery mode, when the power fails, since the rectifier has been turned off, so the DC-DC converter need to help regulate the DC link, and a voltage loop is added. Similar average models are also built for other power converters like the power supply units and the variable frequency speed drive used in the air conditioner. Also, the server load and cooling load are also modeled, which are dependent on the server utilization rate. Okay. And the second step is to derive the discrete model that is compatible with the HCB. So we know that the data center power emulator will be implemented in the HCB, and all the data center model and control functions are implemented in the VSI, in the converter DSP controller. So therefore, the average model we derived before need to be transformed into discrete time version by digitization. Here, we have transformed the model into the discrete time version with the sampling frequency at 10 kilohertz, which is used in the HTB system. For example, I show here, the PI controllers are transformed in this form, and this is the model for the UPS converter. Similar models are also derived for other power components. In addition, we know that the data center has many different power stages. So to coordinate all these power stages, and also have a generalized model in different operation cases, we proposed a generalized model for the power emulator. So as you can see in this picture, the model will start with the terminal voltage and the grid frequency, and then a top-level control will determine the operation modes according to the voltage level. Then the operation mode and the voltage will pass down to the following stages. For each of the stage model, the input variable is the output voltage from the former stage. However, the output variable is the calculated input current, which will also be passed up to the former stage. So I have labeled the different power flow paths in different colors to show the operation and the power flow in different operation modes. Finally, the top level control will update the grid terminal current and starts the next cycle of the calculation. So in the hardware implementation, one sampling period on the DSP corresponds to one cycle through the model. So with this, the third step is to develop the model into the HCB. So in the HTB, all the interconnected power converters share the same DC bus at 200 volts, and they can be configured into different power components. So here, I used a local network consisting of 3 voltage source inverters in one cabinet to verify the power emulator. So the first VSI is implemented as a generator emulator to represent the grid power source that is connected to the data center emulator through a line impedance. And then the data center emulator is implemented by VSI2 and VSI3, serving as all-in-one load. In each of the load VSS, the conditioning function and the data center model, as well as the inner current loop, are all embedded in one DSP. Then the conditioned voltage is sent to the model and generate the current reference, which is used to control the converter, so that we can represent the power performance on the terminal, on the grid terminal. So the specifications of the voltage source inverter under test is shown here, and this picture shows the testing waveform at the steady state with the normal grid terminal voltage. As you can see, the normalized power has the non-unity power factor. This is mainly because the reactive power is generated from the cooling motors in the system. So as the most common grid disturbance, voltage sag events are demonstrated here to show the dynamic response of the data center load. Here I showed both the simulation results in the MATLAB Simulink and the experimental emulation waveforms of the normalized terminal voltage, power, and the onboard power supply AC and DC voltage. So the first one is a voltage sag event when a 25% voltage drop happens. So the data center actually operates from the normal echo mode to the double conversion mode. And the UPS switches in to carry the heavy server load. As you can see, there is a transient response with an abrupt power variation and a slight voltage fluctuation on the terminal. At both the beginning and end of the voltage sag, the data center actually performs transient power change due to the voltage change. So as you can see, if we compare the simulation and the experimental result, we can find they are slightly different. Actually, the experimental result is more realistic because the gate voltage gradually drops or increase instead of a sharp change in the ideal simulation. But overall, the waveforms between the experiment and the simulation are consistent, which verifies the accuracy of the power emulator. The second one shows a more severe voltage sag event with more than 30% voltage drop. So to protect the power supply, the IT equipment, the data center load actually is disconnected from the grid. So the power drops to 0 after the load shedding. Because the local network is not stiff enough. So you can see the voltage actually has some waning and then increase to a higher level after the load shedding. So compare the simulation and the experimental results, the gradually dropped terminal voltage in the emulation is more realistic because in practice, the voltage sag event caused by either the circuit fault or other contingencies is not instantaneous. In both these two voltage sag events, we can see that the DC power finally sent to the server load are held in a high level so that the server load is not influenced. I think that's the main part of my presentation. So I will conclude the work. So in this work, a data center power emulator is developed. We've proposed a complete data center power model and a generalized discrete model to implement it into the HCB platform as an all-in-one load. So the advantages of the proposed data center emulator includes, first, it is able to emulate the dynamic performance of the data center and the regional power network accurately. Second, actually the power emulator's power rating can be scaled flexibly because all the control loops are designed in PO system. So we do not need to redesign the control parameters. Third, such converter-based power emulator is more accessible and can be flexible installed in the HCB in different bus terminals so that we can perform different local or large-scale power system experiments. So in a word, the proposed data center and power emulator provides an effective, accurate, and easy-to-use alternative to the physical data center prototype so that we can better study the power system and the dynamic performance. So with this, I would like to end my presentation and give the acknowledgements. Welcome any questions. Thank you.
Thanks, Jingjing, for the great presentation. So let me check if our students or audiences have any questions. So feel free to unmute yourself. I see October here, unmuted.
Sure. So Jingjing, what sort of behavior can you model with your emulator that other models can't?
Oh, that's a good question. So I think, as I said, so this power emulator is able to predict the dynamic transient performance. So compared with the existing work, the power transient response, like during the server load change, so this model can be can have a more detailed power dynamic response. I mean, you can compare it with the existing work. You can see the transient waveforms in the terminal voltage or the power. However, the existing work can only predict the static performance, and they do not have detailed modeling of the converter and closed loop controls, so they cannot reflect the transient power or voltage change on the grid terminal.
What sort of data center behavior can your emulator not model?
Not model.
The limitation of it.
Oh, you mean the limitation of the power emulator?
Yes.
Oh, well, I think for this power emulator, because I implement all the system model into two voltage source inverters, so I cannot check the internal operation within the data center power stages. Let's say here. For this current power emulator, I can only see the performance on this grid terminal, but the interactions between the different power stages, I cannot check for now. But we can implement in different voltage set in different inverters. I mean, split the whole data center model into different inverters and check their internal operation performance.
Great.
Okay, that's all from me.
Okay,
Thank
thanks,
you.
Dr. Tolbert, and thanks, Jingjing. So we will need to move on. Thanks, Jingjing, for your presentation. So,
Thank you.
so we will move on to our next presentation by Dr. Jin Zhao. The title is Spatio-temporal Coordination of Load Restoration, Considering Renewable Energy Participation. Dr. Jin Zhao received the BE and PhD degrees from Shandong University, Jinan, China, all in electrical engineering in 2015 and 2020, respectively. She is currently a postdoctoral researcher at the University of Tennessee. She was a research assistant at the University of Hong Kong and was a visiting PhD student and postdoctoral researcher at the Technical University of Denmark. Her research interests include power system resilience, transmission distribution system restoration, renewable energy integration, power system optimization, deep learning, and reinforcement learning. So let me turn the presentation to Dr. Jin Zhao.
Okay, let me share my screen. Okay, here we go. Can you see the screen now?
Yes, yes.
Okay, so thank you for having me. It's quite a great honor for me to share my research here. So my name is Jin Zhao, and I just joined in the Enlighten Lab supervised by Professor Fran Li at last year, December. So today I'm going to share a part of my PhD student work when I was a PhD student. So we're going to talk about the spatial-temporal coordination of the load restoration considering the renewable energy concentration. So first, I'm going to give a brief introduction about the background of my field, and we will quickly go through 3 questions that will help us understand and give a solution to the corresponding problems. And finally, there will be a summary and some extending studies of me. Okay, so my field is actually the power system restoration. So the PSR is actually a process of restoring the system back to a normal operation condition when there is a partial or complete blackouts. Specifically, I mainly focus on the load restoration part, which is the last stage of the whole restoration process and also the final goal of the PSR process. So our goal is actually to pick up as much and as much loads as possible, and both we wanted to bring back all the loads as soon as possible, and facing with the time varying and limited power supply condition. So in the step-by-step load restoration process, we may want to obtain a strategy which will help us to solve the problem of when, where, and how much. This means if we get the strategy, we can give some guidance about when can we bring back the loads and which part of the loads can we pick up, and also how much is the restorable load amount. Okay, so the consideration of renewable energy sources is actually inspired by the recently happened several worldwide blackout events related to renewable energy. In 2006, there is a blackout event in the European system. And after the blackout happened, the system actually separated into 3 parts. And in the restoration process of the Northeast region, there happened unplanned reconnection of wind turbines. This action of wind turbines actually led to a chaos of the power flow in this region. And finally, we can see there is a lot of overloaded conditions in the grid and bring some troubles in the restoration process. Okay, so in the 2016, the renewable energy is actually become a main reason that led to the blackout events in the South Australia system. You can see that before the events, the wind generation in this region had almost reached to 15% of the whole energy. So this become a very important part for the power supply. So when the unexpected tripping of wind turbines happened after the extreme weather, this part of grid will totally break down. Similarly, in the 2019, in the UK outage event, the unexpected tripping of the Hornsey wind turbines brought indispensable power supply deficiency in this grid and become one of the reasons to lead to the outage event. So according to the former events, we can concluded that, of course, the renewable energy become an indispensable part of the power supply in our grid, and we cannot bring back all our loads if we do not use them. And on the other hand, the application of them should be reasonable, scheduled to avoid the bring some queues in the restoration process. So the question is, how can we use the RES in the restoration process? Basically, we will solve 3 questions under this topic, and start from the transmission system. We will discuss how can we use the large-scale clusters of the IES in the transmission system. And then we will extend to the distribution system and to discuss the problems in the coupled transmission and distribution system. And finally, because the load restoration is a quite a long time horizon process, so we may want to do some multi-step coordination in the whole process. Okay, so here we go to the first problem, how to use the IES in the back system load restoration. As we all know that the RES, such as wind power and PVs, they both have the characteristic of flexibility and uncertainty. That means they are a kind of power sources with very little startup time limitations. And this point will give a great help to the PSR process. However, their output is uncertainty. So that means they are a kind of undispatchable in the restoration process. Conventionally, when we make decisions in the PSR process, we may based on dispatchable power sources and also accurate load forest. However, when we consider in the integration of IES, we may have some uncertainty on the power output, both in the power supply side and the demand side. So if we still make a decision assuming a determined environment, the result maybe bring some risk about the frequency and voltage constraints violations. So our objective may be changed here from just pursuing the largest load recovery amount to considering a kind of risk control. So under this condition, on one hand, we wanted to use the IES to improve the efficiency of the load restoration process, because they will definitely bring more available power supply for us. However, on the other hand, they will have some uncertainty problem and lead to the security problem. So how could we make decision under these decisions? Under these conditions. And here we propose the concept of utility. The utility means the return minus the risk. For our problem, we can define the return to be the expected load pickup amount under a certain load restoration strategy. And the risk could be the possible power deficiency with the same strategy. So we can make a model to build the utility-oriented optimization model. And applying this model, we may have a good balance between the efficiency and the security. And we can always tracing the power deficiency under uncertain conditions. And it can also provide the ability to reflect the risk attitude of operators by setting different confidence levels. Okay, so the technical part of it do some extra efforts because the original model is quite complex and non-convex. So we do some extra work to make it finally to be a linear programming model, which is obviously very easy to be solved. So we use this model to realize the decision-making under uncertain conditions. We will obtain the online data, and then the operator will set a confidence level to reflect their risk attitude, and we use a utility-oriented model to provide the final strategy, which will guide us how to use the wind powers and solve the problem of when there are how much questions. And this model is because it has a simple mathematical type, so it is very fast. The solution of it is it can be solved really fast, and we can get the strategy just directly based on the online data. This part of work has already verified using an IEEE 30 bus system. This shows flexible usage of our proposed system, and also it has verified using a real-world system, which is a part of the grid of Shandong province, China. It also shows flexible, robust adjustment ability on the different online data with different exact needs. Okay, so by using a utility-oriented management method, we have give a good guide to about how to apply the IES in the bug system. However, we all know that the IES, they have a large amount of them are actually concentrated at the distribution levels as the distributed energy sources. So we may use this part of source to further speed up our load recovery process. And here comes some problems, because conventionally the study of transmission system, which is TS restoration, and the study of distribution system restoration, they are separated. However, this separation has already brought some security problems, such as in the 2011 in the Arizona South California outage. This is because the neglecting of the lower voltage level grid operation, which brings some troubles in the restoration process and further delayed the process. So why we wanted to do a coordination between the transmission system and distribution system? That is because we wanted to avoid the security problem caused by neglecting the distribution system operation. And we may want to use the available resources in this slide to further speed up the load restoration process. Considering this, and direct idea to realize this is maybe we can build a centralized optimization model that can include both the transmission side and distribution side. However, these may bring some problems like the data processing burden of the distribution system side, and also there is some information privacy problems of different system operators. So a decentralized scheme may be more suitable for our problem because it allows independent decision making of different system operators, and at the same time it can provide a global optimal result for the whole system. Okay, so the key to realize the decentralized scheme is actually the decoupling of the physical structure between the transmission and distribution system. We actually do some mathematical transformations to make up original united model to be an up-level model presents the transmission system, and also several lower-level model to present the distribution systems. And the up and lower level models, they will have an iterative calculation process, which is actually a decentralized decision-making process. Because in this process, the lower level distribution system operators will just consider their own requirements for load restoration and provide a power demand to the up-level transmission system level. And the transmission system operators will consider the power demand from distribution system operators, and also it will consider their own problems to give a reasonable power supply. This iteration process will end until the until all the system operators reach to consensus. However, remember that our problem is quite complex because we may consider both the TS and the DS side power flow, and we have limited power supply. And also one point is so important that we have tremendous binary variables because we have to decide the pickup decision of load. So this makes the model quite complex and will have some troubles about convergence. So in this part, we have further improved the algorithm to make the final result have a convergence guarantee, even though we have a complex model with integer variables. And also we do some simplifications of the mathematical programming models and reduce the calculation skill of them. This part of work is first verified in T116 and D30 system. This is a quite large one because it contains the 118 bars transmission system and 33 bars distribution systems. And obviously our improved algorithm have a good computational behavior because it has a better convergence behavior and less computation time. And the decentralized scheme is also applied in the real world system, which give a really good performance because it has obviously speed up the whole load restoration process. This is because we have efficiently used the available power supply from the distribution system side. Okay, so in the former researchers, we have dealt with the application of RES programs both in the transmission side and distribution side. However, remember that our load restoration problem is a long time horizon process with a lot of steps. So we may want to do some coordination between the steps to give a better result. Even though generally we just focus on a single step optimization and we will recursively use this model to complete the whole process. However, our condition now is actually we have a lot of RES in the system and there is cold load pickup phenomenon bring some troubles. So we may want to have a longer time horizon scope in the process to deal with the uncertainties of RES and the load and also realize the coordination of multi-steps. So we've proposed receding horizon load restoration framework. This is actually based on the MPC method. In short, it is actually look forward for several steps, but we just implement the current one. And obviously, we have not solved the uncertain problem. So extra efforts have done to deal with this problem. We have used a conditional value at risk method, and the mathematical characteristic of it can help us to give a sufficient power supply consideration for the decision-making process. And also there is a two-stage process for the optimization model. This is because it is really hard to solve a multi-step one. So we find some way to relax the multi-step optimization model and use the result of the first stage as a reference to the second stage. And in the second stage, we just consider a single step model, but with a strict constraints to give an accurate result. And in this part, we have used the same testing system with the decentralized research, and the proposed method have obviously a great benefit in the computation time and acceptable load recovery performance, and also in the real-world system, the multi-step coordination actually give a more flexible application for the renewable energies, and it finally speed up the whole restoration process. Okay, so this is the 3 questions that we've solved, and we should always remember that in the process, we wanted to obtain the strategy to solve when, where, how much problems about the load recovery. So firstly, we do some uncertainty management to help the operators make a decision on the uncertain conditions. And then we give a spatial coordination by considering both the transmission and the distribution side. And finally, there is a temporal coordination to help us obtain a longer time horizon scope for the whole restoration process. And the solution of all these problems finally help us to realize the spatial-temporal coordination of PES concentrated load restoration process. And because of the time limit, I did not go to the detail of the technical part. So if you are interested, you can read 3 of these papers. We have give everything that I've talked about just now. And also I have do some other extending studies about the distributed and decentralized restoration. So if you have any interest, you can go to these papers, and you are welcome to contact me if you have any problems. Okay, so I think this is all for my sharing today, and thank you so much for your attention. And is there any questions?
Thanks a lot, Jin, for the presentation. I think we're running out of time, but let's see. We can accommodate 1 question. See if there's any question from here. So let me ask a quick one. Like, have you encountered those infeasible scenarios, and what kind of relaxation or techniques did you use to resolve them?
You mean, did I give some open source techniques?
Oh, no, I mean, when you formulated your optimization problem and try to solve it, did you run into any infeasibility? Unsolvable.
Actually, I am focused on the steady state. That means I just I need to calculate the power flow calculation. So this may, it's like a kind of benefit for me to have little problems about the technical part. Yeah, this is not related to the dynamic something. Yeah.
Okay, great. So if there's no more question, I think we're running out of time. So that concludes our seminar today. So thanks everybody for calling in, and thanks to our presenters, and we'll see you next week. Have a great weekend.
Okay, thank you. Bye.
Bye.